Hey, it's Ben, and you made it to Lecture 4 of Open Project Space. We're talking about microcontroller architecture and, at last, Arduino. But before we cover those topics, we'll begin with what will feel a bit tangential, but I promise you by the end of the lecture, you'll see how this relates. We're talking binary numbers and digital signals. So, you're familiar with the decimal number system. That's the system that we use to perform any sort of mathematical computation, the one we use in our everyday life. It contains a set of 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And because there are 10 digits, that makes it a base 10 number system. Again, the decimal number system, the system we use most often, is a base 10 number system. Now, there exist different bases beyond the decimal number system. For example, base 8 is the octal number system with a set of only 8 digits. That's 0 through 7. We could get bigger. Base 16, or the hexadecimal number system, has a whopping 16 digits. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then we run out of our typical symbols, so we use characters like A, B, C, D, and F to represent what would be 10, 11, 12, 13, 14, 15. That's 16 digits in base 16. Now, we can actually convert a number of a different base to base 10 with the following method. Let's say, for example, we want to convert the hexadecimal number B32 to base 10. Now, take a note of this subscript here, 16. This indicates that the number here is base 16. 16 is hexadecimal number. Now, the first thing that we're going to do is take our digits of the hexadecimal number and expand them. We're actually going to multiply each of these by 16 raised to the power of some number. 16, again, is the base of the number which we are converting. That base is base 16. Now, what's that power? And I think the best way to explain this is to give an analogy of the base 10 system. The first digit of any base 10 number is the ones place. That's 10 to the power of 0. That's 1. The second digit would be the tens place. That's 10 raised to the power of 1. And then the third digit would be the hundreds place. That's 10 to the power of 2. So the same principle applies to these hexadecimal numbers when we're converting them to base 10. For our first digit, we multiply it by 16 to the power of 0. For our second digit, that's to the power of 1, 2, and then so on and so forth for each succeeding digit. And again, each hexadecimal digit represents a power of 16. So now we're going to do some basic math here. Multiply 2 by 16 to the power of 0. That's just 2 times 1, which is 2. And we're going to do the same thing for our next digit. We get 48. But now what we want to do is convert our hex digit B to base 10. So if you remember from the earlier slide, we have hexadecimal digits 0 through 9, but then we run out of characters, so we switch over to letters. A represents 10, and so then B represents 11. So we're going to replace B with 11. And now we can finish our computation multiplying 11 by 16 to the power of 2 and adding our numbers together. Again, B is represented by the decimal number 11. When we add these all together, we get that the hexadecimal number B32 is equal to 2,866 in base 10, or decimal. Let's pivot just slightly here. Jumping back to computers. Computers transfer data across electrical wires or lines, and they do so as digital or discrete voltage signals. These signals are either a high or a low voltage. They're part of a discrete range of values or voltages that can represent these signals. Again, it could either be high or low, but nothing in between. And this would contrast from an analog signal, which can be values in a continuous range. Let's say that continuous range is between whatever we define this high or low voltage to be. So again, we have a digital signal here. You should recognize this from a lecture or two before. In this digital signal, the waveform is either the value 5 volts or 0 volts, two discrete values, 5 or 0. These digital signals are translated to the binary number system. Now we're coming back to number systems. And that binary number system is base 2. We have 2 digits. It's either 1 or 0. Let's expand on binary a little more. So single binary digits are called bits. Bits compose binary numbers like 1, 0, 0, 1, 0. That would be 18 in decimal. If we take 8 bits and put them together, that forms a byte. So here are 8 bits here. This is a byte. This is another byte. And again, each of these convert into decimal numbers. Now, data in a computer is stored in hardware that we call memory. And memory is divided into cells, each a byte in width. That's 8 bits per cell. So take a look at this visualization here. Let's say we have this memory hardware. This memory is divided into cells. Each cell stores just a byte. And so that means when we're accessing memory, when we want to access data and we go to a cell of memory, the smallest unit of data is a byte. But we can get a lot bigger than bytes. Decimal units are used to express the size of binary data. So 8 bits form a byte, but then we have a kilobyte, which is 1024 bytes, and then a megabyte, which is 1024 kilobytes, and we have gigabytes and terabytes. And I bet a lot of these terms look familiar now. Your files on your computer might be kilobytes, might be megabytes. You put enough files together in a folder, it might be a folder that contains gigabytes of information, and maybe your entire computer has like a terabyte of storage space. And let's talk more about that scale between different computers. Small embedded computers, like a handheld calculator, may store just kilobytes, or maybe, if you're lucky, megabytes of data. Now, your laptop, again, might store gigabytes or terabytes of information. But then let's say Google servers, which basically run the internet, store exabytes of data. That's billions of gigabytes. So now that we've discussed number systems and how the binary number system relates to computer technology, that will provide us a steady basis to go and talk about microcontrollers. A microcontroller, or MCU, is a small computer on an integrated circuit, like one of these. And I mean quite literally, a microcontroller is a computer. It's complete with everything we need to run and store programs. Now, something we had brought up in a previous lecture was that different computers run off different architectures. And an architecture is what defines the organization of hardware within the computer. We also mentioned in the context of programming, if a computer has a different architecture, the programs that run off of it, the programs which are made up of instructions, will require a different instruction set tailored to that architecture. So, just like any other computer, MCUs, microcontrollers, have different architectures. And when they have different architectures, sometimes we might say they belong to different families. So all of these ICs, despite the different packaging here, like this one is surface mount, this one is through hole, they are all part of the same family of microcontroller. In fact, our discussions will focus on a microcontroller which adheres to the AVR architecture, microcontrollers which are part of the AVR family. Now, this microcontroller that we're going to talk about runs programs made with the AVR instruction set. And to better understand how an AVR microcontroller works, we're going to examine its key components. So the main units of an AVR microcontroller are the central processing unit, memory, an analog to digital converter, timers, input-output ports, and serial communication units. I just threw a lot of terms at you. We're going to break it down, I promise. So here's a visual of all of this. We have a big unit here, which is interconnected with all of the other ones. Now let's go through the definition of each unit in this AVR microcontroller. Let's start with the central processing unit, the CPU. Now, the CPU executes the instructions from our program, and those instructions are provided by a memory unit. These instructions may be mathematical computations, they might be memory data transfer, or these signals to inputs and outputs connected to our input and output ports. So that memory unit stores data and those program instructions we mentioned before. There are subunits of memory, some of which are for short-term storage, meaning they're erased when the microcontroller is disconnected from its power source, and others are for long-term storage. They survive when the power supply is disconnected. Long-term storage is usually for stuff like our program instructions. We don't want them being erased between the power cycles of the microcontroller. A power cycle being when the power supply is turned off and on again. Then we've got those input-output ports, or we'll call them I/O ports. These connect the microcontroller to peripheral devices that transfer data to and from the microcontroller. Now, this data may be stored in memory, or it will eventually be interpreted by the CPU. The I/O ports are wired to physical leads on the IC. These are called I/O pins. We're going to use those I/O pins to connect to our peripheral devices. Then there's the analog to digital converter, or ADC. This measures real-world analog signals from the I/O pins. That might be temperature, pressure, or acceleration, to name a few. And it takes these analog signals and converts them into digital signals that the microcontroller can interpret. And guess what kind of digital signals they'll be? They're going to be binary signals, ones and zeros. We have timers. Timers will be used by the microcontroller to control the timing of program execution, or maybe output signals, and timers can also be used to measure time. We have all these last units, the TWI, the USART, and the SPI. They are all what we call serial communication units. They're units that generate and interpret serial communication signals between the microcontroller and those I/O peripherals. This is going to facilitate the data transfer across devices. We're going to expand on these terms, especially serial communication, in a future lecture, I promise you. But for now, we're going to move on, having discussed those core hardware components of the microcontroller. We're ready to talk about Arduino. The Arduino company designed microcontroller boards to make AVR MCUs hobbyist friendly. So what they did here was they took a DIP IC version of the AVR microcontroller and they put it in a DIP socket on this larger board, this PCB. And what they did was they added a USB port. They added input voltage regulators. They added some onboard LEDs, among some other things like pin headers. And again, this is all with the intention of making it friendly and more accessible to people who are trying to rapidly prototype their projects with the AVR microcontrollers. And so this includes a family of boards. This is the Arduino Uno. There's the Arduino Nano, that's a smaller version, and there are many, many more. So I just brought it up, but again, there's the Arduino Nano, and this will be an area of focus for the current lecture and future lectures. It's based on the Atmega 328P microcontroller. This microcontroller is part of the AVR family. In fact, Arduino Uno uses the same microcontroller. So if you're in a position where you're following these lectures and you have available to you an Arduino Uno, that's perfectly fine. Almost all code you write for the Arduino Nano is going to be directly transferable to the Arduino Uno, if not all code that you write. And again, over here, you'll see instead of a through-hole DIP IC packaging, we have the AVR microcontroller here that is a surface-mounted microcontroller directly onto the Arduino Nano PCB. So remember, microcontrollers are computers, and like any computer, it has to run programs that we are going to write for them. And in order to write these programs, we will use an IDE, the Arduino IDE. Just have a couple of steps to set it up. The first of which will be to install this driver, the CH340 driver. That's going to allow our computers to understand communication with the Arduino board when we connect it via USB to our computer. And you can download that installer here. If you go and interact with the PDF format of the slides, it will give you a web page with some links to some different formats of downloadables for you to go and install on your computer. Of course, we need to install the Arduino IDE. This is going to be where we write our code, compile it, and upload it to the Arduino board. And you're going to install that IDE here. It's going to take you to a page, something like this, with your download options. Go ahead, download and install the CH340 driver, the Arduino IDE, and once you're done with those steps, follow along with the rest of the lecture. When you first open up the Arduino IDE, it's going to hopefully look like this. You have a code editor, just like any other IDE. You have a menu, there's a sidebar here, but we're going to focus on the code editor for now. This is our default source code file when you first open the application. And these source code files in Arduino are called sketches, and they end with the extension .ino, I-N-O. Let's say you open the application and there's already some code there, maybe from your previous session. If you wanted to make a new sketch, all you have to do is click File and then New Sketch. So let's say you want to edit a sketch. Well, you'd go ahead and open up that code editor again. When you first open the application, it will start with some template code. These are two built-in functions which you have to go ahead and define as the programmer. And when you type, it will actually give you some auto-completion or tooltips like here. And that's about the gist. It's not too crazy as a text editor, but the more complicated component comes when we want to actually upload a sketch to our board. When we want to take the program, put it on the Arduino board, and run it. Before we can upload a sketch, we've got to connect the Arduino board via USB to our computer, and we're going to configure the IDE to the correct board and USB port. So ideally, the easy option will work, which is to go ahead, open your IDE, select the Select Board dropdown, and there it is, Arduino Nano. That's what I want to connect to. My computer recognized the Arduino Nano. I can go and select it, and then I'm ready to upload code. Let's say that doesn't work out, and we have a situation in which, what just happened there? Yep, no Arduino Nano. And so we can go ahead and select other board and port. It's going to open an additional menu. And this additional menu will have you select manually the board of your choosing. We are going to go down to Arduino Nano and then select from one of the available ports. Now, I know this isn't the correct port, but let's just assume it is. For whatever reason, the IDE just didn't recognize this as an Arduino Nano, so we can go ahead, select this port, and click OK. Now, we've got to verify and upload our sketch. Before uploading the sketch, let's verify. You click the check mark icon here, and we can compile the sketch. Let's say the sketch compiles successfully. Then we can upload it using the right arrow here to upload the compiled sketch to the Arduino board. Let's see what that looks like. Let's say we've got our program here. This is an empty program, but it'll work nonetheless. We hit verify. It's going to open this pane down here that's going to give us some information about the compiler. It said done compiling, must have been a success. And we could go ahead, hit the upload button. It's going to compile the sketch again, but this time it's going to upload as well. And it seems to have been a success. So there's nothing to it really, unless something happened and the upload timed out, or active ports are missing from the dropdown. Here's what you're going to do. You want to first check your USB connection between the Arduino board and your personal computer. Is your system's device manager showing that the Arduino is connected? If that's not the case, that's not a good sign. You can do two things after. One is you can check the USB cable by replacing it, or you can switch to a different USB port. Sometimes your CH340 driver may have not been installed as you thought it was. And after you go through any of these steps, just go ahead and restart the IDE, maybe even your personal computer, and hopefully that'll be resolved in steps 1 through 3. But if you reach step 4, this is the phone a friend option. Go ahead, look it up online. There are so many reasons why an Arduino might not be recognized by your computer, and so many solutions out there. So we've talked about the Arduino IDE, given you that quick crash course. Let's talk about the pins on the Arduino board and their functionality. So here's a pinout diagram. This isn't the first one you've seen, and this won't be the last. A pinout diagram is included in the Nano datasheet, and a lot of these pins on the pinout are general purpose input-output pins. These are pins with no predefined purpose. As the programmer, we're going to design an Arduino sketch to control these pins. We're going to give them purpose. These are analog and digital pins. You can see they run along each side of the Arduino board, and there are plenty of them. Sketches will control our pins. Sketches are written in the Arduino programming language, which is conveniently basically C++. We will assign pins as global variables at the beginning of our sketch. And notice the syntax, exactly the same as C++. And an important note here is that each GPIO pin is associated with an integer. So each pin here on the pinout, it's got an integer value in the Arduino programming language, and we can use that and pass it into some of the Arduino's built-in functions in order to control those pins. So a good practice here is to assign each pin we'll use as a global variable at the top of our sketch. The pin name should be whatever the purpose of the pin is. Let's say it's controlling an LED, call it LED. And then you want to assign LED, that variable, to the pin number. So here's what we're going to do in the setup function. We need to set the pin mode of each digital pin we use, and so we'll call the function pin mode. It has no return value, but it does take 2 arguments. We'll pass the global variable we assign to each pin for the pin parameter, and then we will also set the mode. Mode is one of 2 constants. It will either be input or output. As a general rule, we're going to read data from input pins. So if you're reading data from a pin, set it to input. And if we're taking data and sending it to the pin, that's going to be an output pin. And we have 2 examples of that here. Here we've set the pin mode of our LED pin to output. The next one we set to input. Now what's this thing over here? This is a call to a member function of the serial object, which facilitates communication between the Arduino board and the computer connected to it via USB. So I promise I will elaborate on how this works in the future, but for now, trust me and pass the value 9600 as the only argument to this function. Again, we'll cover it later, but whenever you use setup, call serial.begin and pass 9600 into it. Let's talk about digital and analog pins, starting with digital pins. If you were to take your Arduino Nano and orient it so that the USB port faces away from you, you would see digital input and output pins on the right side of the board, and on the left side you would see digital output only pins. Each of these pins are numbered, starting with 2, going all the way up to 21, and that's how you'll identify them in the Arduino programming language when you assign a variable to one of these pin numbers. Now, notice how earlier I mentioned there are digital output pins here, but these are digital input and output. Well, when you go and set the pin mode, the digital input or output pins can be set to either input or output pin mode, but the digital output pins over here can only be set to output mode. That's an important thing to remember as we come across these digital pin functions, starting with digital read. What does it do? It reads the voltage at the input pin you pass into this one and only parameter, and it returns either high or low, a high voltage 5 volts or a low voltage 0 volts as an integer 1 or 0. We can also set the voltage at an output pin using digital write. So if we pass the pin number into the first parameter and then as the second choose a value, it's either high or low, we will set that pin to the voltage 5 volts for high or 0 volts for low. And an easy analogy here is to think of digital write as a light switch to the light bulb that is, let's say, connected to this pin. Use a switch to set the bulb to either the max brightness or in the min brightness. The switch goes up for on or down for off, but there's no in between. The bulb is either on or off, high or low. Now we've got those analog pins. If we orient the Nano the same way as we did before with the USB port facing away from us, on the left we'll see these analog input pins. You'll notice these analog input pins are some of the same pins as the digital input pins I showed you a couple slides before. It's because pins have multiple purposes. These pins, these analog input pins, have their own aliases. Instead of 0, 1, 2, 3, and so on, we use A0, A1, and A2. A0 is what we would set our analog pin variable in the Arduino programming language to, as opposed to 0. And that's how we distinguish between our analog pins and our digital pins. You don't want to get in a situation where you've used 2, expecting it to be digital pin 2, and 2 somewhere else expecting it to be analog pin 2. There's an ambiguity there that's resolved when you use the alias A2 instead. And on the right side, we have these PWM capable digital output pins. I promise I will tell you what PWM is, but for now, just know these pins are indicated with a tilde beside their name. So let's talk about some analog pin functions. First thing we might want to do is read the voltage at an input pin. And this analog read function will do just that. We pick a pin, and what it'll do is read the voltage and map it to a value in the discrete range 0 to 1023. And that represents the voltages from 0 to 5 volts. So 0 volts was 0 in the discrete range, and then 5 volts is 1023. And then analog read returns that mapped value. And again, when you use analog read, use the aliases A0, A1, A2 for the pin number instead of 0, 1, 2, and so on. And for analog write, we can set the average voltage on a digital output pin to a value in the discrete range 0 to 255. And that would be from 0 volts to 5 volts. So no longer are we restricted by digital write's high voltage or low voltage only. We can get values like 1.2 volts, 3.5 volts in this range. And this is a function for PWM pins only. So the only pins that analog write will work on are these PWM capable digital output pins marked by the tilde on the pinout diagram. So here's another analogy to describe analog write. Think of it as your light dimmer. You might have a slide that you can set the bulb to a brightness anywhere between maximum or minimum, and you can use the slide to get somewhere in the middle, somewhere closer to maximum brightness, or somewhere lower. You're no longer restricted to that on switch, which is only max brightness, and that off side of the switch, which is minimum, or for a light bulb, no brightness. So you are no longer restricted to those binary values, high or low. You can set the bulb brightness in a continuous range of values. Now, a note on analog read. Analog read utilizes the analog to digital converter, the ADC, inside the Arduino's AVR microcontroller. That's what measures the real-world analog signal and converts it to a digital signal. So why is it that analog read outputs values between 0 and 1023? 0 again is supposed to represent 0 volts, read at the input pin, and 1023 is supposed to represent 5 volts. Why is it limited to this range? Well, the resolution of the ADC on the Arduino Nano is just 10 bits, which is why the function only returns values from 0 to 1023. If you have a number that is only 10 bits, the highest 10-bit number you can get is 1023. Here are some more functions you can use. We've got delay. Delay pauses the program execution by ms milliseconds, ms being that input parameter. So if you pass in 1000, then you delay the program execution by 1000. Literally, when you call delay, it pauses the program, and then when it's done, it resumes and goes to the next line. We have two more member functions from serial. The first of which is serial.print. What it does is it takes that input parameter val and it sends it to the computer connected to your Arduino board via USB, and it displays the value on the serial monitor in the IDE. I'll show you what the serial monitor is in a moment. And we also have serial.println. It does the same thing as serial.print, but when it displays the value on the serial monitor, it follows it with a new line. So let's talk about that serial monitor. When your board is connected to your personal computer via USB, you can select the serial monitor, that magnifying glass icon in the IDE. And a pane will appear at the bottom of the IDE window, which displays all the data sent by the Arduino board using serial.print. So let me show you that quickly. By pulling up the IDE, we have our application open. We can go over to the top right corner where the magnifying glass is. We click on it, and there's the serial monitor, and all the text that's sent from your Arduino will appear here. In the absence of a debugger, and the reason for this is the Arduino Nano is not capable of using a debugger, we want to use serial.print as a tool to help debug our programs. So let's say you have some variables. If you print the values of these variables throughout parts of your program, when it's displayed to the serial monitor, it might help you notice when the variable values unexpectedly change. And when they do, you know there's an error and you have an idea of where in your code it might be. And now another important note here is that the C++ IOStream library is not compatible with Arduino. So don't use streams like cin or cout to print text or to input text. Just use serial.print. That's the primary way you'll print text to the serial monitor. The way serial.print works is fundamentally different. It's actually sending data from the Arduino Nano to the computer over USB. A great resource available to you as you expand your knowledge of the Arduino programming language is the Arduino reference library. You can access this link through the PDF form of the slides. The Arduino reference library is going to show you more functions that are built in, and you can also check out additional libraries that support devices like LCDs, other sensors, and even stuff like Wi-Fi modules. So go ahead, check this out later, learn more. We are going to talk about one more big concept before we move into some live demonstrations with the Arduino board. And this concept is pulse width modulation. So the Arduino board, and really it's the underlying AVR microcontroller, is a digital source. It can only output a high or low voltage, 5 volts or 0 volts, which raises the question, how does analog write output analog signals? Earlier we said that analog write can output voltages like 1.2 volts or 3.7 volts. This is done through pulse width modulation, PWM. It is an oscillating digital waveform that emulates an analog output. By oscillating a signal from high to low very fast, the average voltage over time will be between high and low, which is an analog value. So let's say we have this square wave. Well, the average value across this square wave over time is going to be 2.5 volts. That's an analog value that we've created from this PWM wave. So the duty cycle of the PWM wave, which is the percentage of time where the signal is high, will determine that analog value. For example, a 50% duty cycle is going to translate to an average value of 2.5 volts. That's what I just showed you earlier, where we had a square wave. The average value is 2.5 volts. This same concept allows us to output a continuous range of voltages between high and low. So if we had a 25% duty cycle, then the average value is somewhere closer to 1.3 volts. If we did 75% duty cycle, then the average value of the waveform would be somewhere closer to 4.3 volts, something like that. So it's really this average value of a digital waveform that emulates an analog signal. Now remember, in the AVR microcontroller, we have timers. Timers are what control the duty cycle. Timers are what help us time the digital waveforms so that we can achieve these different analog signal outputs. So with that, let's get started with some small exercises where we actually use the Arduino board. To prototype our circuits with the Arduino Nano, we'll seat the Arduino Nano along the DIP channel of your standard breadboard, just like you would a DIP IC. And the Arduino Nano's USB port should be oriented away from the board so that the cable, when you plug it into the port, doesn't obstruct the other components on the breadboard. And as a final note, when you build circuits that interface with the Arduino board through these pins, they have to share a common ground with the ground pin of the board. So you see the ground pin right here, and you also see it labeled in the pinout diagram, of course, and on the physical board. So let's start with our first interactive demonstration. We're going to build this circuit, complete the template code, flash it to the Arduino board, then verify the circuit. That circuit is just a simple digital LED circuit. We are going to use the sketch to light the LED. So let's open up the IDE, and we're going to start with this template code. And at the very top, what's the first thing we do? We assign variables to each of the pins we're going to use. That'll be const int. We've got an LED pin, and on the schematic I see we're going to use the D5 pin. That's 5 in the Arduino programming language. Then we're going to set our pin mode of the LED to an output, because we're outputting a voltage to the LED. And then we're going to go into our loop. What we're going to do is use digital write. We want to set the voltage of the LED to high so that it turns on. So the code is basically complete here. Before we verify and upload, let's set up our circuit. I've taken the liberty of doing it ahead of time. So we have the Arduino Nano. It's connected to my computer via USB. We have the LED circuit here. The LED is connected to pin D5, and the resistor is connected to the ground pin of the Arduino Nano. So when I go ahead and hit verify, it's going to compile the sketch. Everything seems to be fine. It's done compiling, no errors. And then we upload. And once it's done uploading, oh, did you see that? The LED turned on. And that's all it took. 1, 2, 3, 4, 5 lines of code. The next one is going to be a blinking LED circuit. We're going to build the schematic again. It's the same one as before, so no setup needed. Then we're going to complete the template code, flash it to the Arduino board, and verify the circuit. And so we can breeze through this. I'm just going to start with the code we had already written for our last demo, but this time we're going to add some stuff to our loop here based on the template code provided. This time we want to oscillate the blinking LED on and off. So I'm going to put up a delay. Let's say it's a delay of 1 second. We don't need the S there, my bad. And then we will use digital write to turn the LED off. And then we'll use one last delay, 1 second. And after that delay, the loop will go over again, start back at high. So if we check out our live circuit, we verify the code. Oh, my bad. There's a 3 here. If we verify the code, it compiles, and then we upload, and hopefully what we see now, after the upload finishes, is that the LED is blinking on and off. And all we needed were 2 calls to digital write with a delay in between, turn the LED on, set a delay, then turn it off, set another delay, and it just keeps looping through it. That's all it is. And so the next and final demonstration will be just a little more complex. So first we'll introduce a new component. This is the potentiometer. It's a 3-terminal variable resistor. It is basically a dial which connects 3 pins. We're going to use the potentiometer as a voltage divider, a circuit which accepts an input or supply voltage, and it's going to output a voltage which is a fraction of this supply voltage. The voltage of the potentiometer's output pin here is going to be in the range of the supply voltage and ground. For our Arduino, because the supply voltage is always going to be 5 volts, that means the output voltage of this potentiometer will be between 0 and 5. And when we twist this dial, it will change the voltage in between those 2 values. So we're creating an analog output signal for the Arduino to read. Internally is a resistive strip. So this is the potentiometer. Here are the 3 pins again. What we have here is a resistive strip between VCC and ground. And so when current travels through VCC to ground, the resistive strip is so high resistance that the current is negligibly small. And so this doesn't short the potentiometer. But we have a rotating wiper, and this is what connects the output pin to the resistive strip. When the wiper is turned counterclockwise and there is minimal distance between VCC and the wiper, that means there is lower resistance between the 2, and so the voltage is higher. But as the wiper turns clockwise to the opposite end, closer to ground, there's so much distance, so much resistance between VCC and the wiper that the voltage of the output pin is now much, much lower. So the wiper reduces the voltage at the output pin the further it's turned clockwise toward ground. Now, an important note here is that the position of VCC and ground can be swapped. These are symmetrical, so you could as easily use the left pin of the potentiometer for ground and the right pin for VCC. You just need to make sure that the 2 outer pins are VCC and ground, and never the middle pin, or you may short your potentiometer and short your circuit. That's the gist. And so now we're going to use this potentiometer to build a dimmable LED circuit. We're going to build the circuit schematic below. This is the schematic symbol for potentiometer. Remember, on this slide, we said the output pin is going to be that arrow pointing into what looks like a resistor, but this is our 3-terminal variable resistor, our potentiometer. And so our output pin of the potentiometer, the middle pin, will be connected to A5 of the Arduino Nano, and will connect ground to this side of the potentiometer and the 5-volt voltage source to the opposite end of the potentiometer, and we'll just have that same LED here. And the goal is when we twist the potentiometer, then the LED will dim or grow brighter depending on the direction. And we do so using both analog read and analog write. So that's using the analog to digital converter and the PWM waves created by the microcontroller. So let's go ahead and do that, starting with a clean sketch. So the first thing we're going to do is create our global variables. We're using 2 pins this time. So first let's declare the pin for our LED. That was D5. We're going to do the same thing for a potentiometer. Remember, it has an alias A5, and that's how we differentiate between D5 and A5. Now we need to set up our pins. We're going to start with a pin mode for the LED, not pin mod, pin mode. That is going to be an output pin. We're outputting a signal to the LED. And as it turns out, we don't need to set the pin mode for the potentiometer. We set pin modes for digital pins. We're using this analog input pin. Instead, we'll just stick with our basic serial.begin function call, and we'll move on to the main loop. So what we need to do is take the input analog voltage from the potentiometer and use that to set the output analog voltage of the LED, or the output PWM wave. So let's create a temp value that's going to represent our input voltage, and that's going to use analog read. At which pin? The pin that the potentiometer's output pin is at. That's A5 over here. The next thing we're going to do is we're going to write analog write. That's how we use PWM. And as our first value, we put in the pin number. That's the LED variable. And then we're going to type in temp. We're going to do something. Remember, the resolution of analog read is only 10 bits. That's 0 to 1023. And analog write accepts a value between 0 and 255. So we need to take a 10-bit value and turn it into an 8-bit value. And the easiest way to do that is to divide temp by 4. Why? Because remember, for a 10-bit value, if the maximum value is 1023, and for, I guess, this 8-bit value, the maximum value is 255, 1023 divided by 4 puts us around 255. So what we've done again is we've read the value at the potentiometer's output pin, we've assigned it to temp, and then we're going to write to the LED a PWM wave with a duty cycle determined by this expression temp divided by 4. We're converting the resolution of analog read to the resolution of analog write. And so, with any luck, what we're going to do is verify the good, success compiling. I'm going to pull up my circuit. You see, I'm still using the blinking LED code, but I've added a potentiometer. The middle pin is connected to A5. The pin to the far right is connected to the 5-volt pin of the Arduino, and the pin to the far left of the potentiometer is connected to ground. And so when I go ahead and upload this code, hopefully we'll get some results. Right, the LED is bright, so that means the potentiometer is set to one side, and if I turn it the other way, it dims. Check that out. A dimmable LED. And with that third demo, I will conclude our lecture. I wish you a wonderful morning, afternoon, evening, wherever you are, whatever time it is. I'll leave you with this interesting misquote, and I will see you all in the next lecture video. Thank you.